Hello, this is Jeffrey Fox, Part M, Cloud Computing and Data Engineering / Big Data. And in this part, we'll do the third group of things about applications on clouds. What jobs can you really run? We had the work we did with NIST on trying to classify applications and understand what does what well when. We have a little discussion of the Internet of Things, and we also discussed different styles of MapReduce. So we can make some very simple statements. Say one of the important issues of clouds, at least original clouds, is no longer so true. Is original clouds were commodity clouds. They had rather poor communication networks and were not terribly suitable for complex parallel jobs. And the type of application that runs well on such systems are what's called pleasingly parallel. You actually take little independent jobs and run them separately on each core or each node. And that's a pretty large sample of data. We can discuss, and if you look at almost all data analysis, it has this structure because each data point is independent, and so you can analyze each data point for the least to try to dig deeply into it independently. There may be some summation or aggregative process at the end which would not be run independently. While there are some problems which we can characterize and understand, which can use classic MapReduce, which does not require significant communication because everything is written to disk. And there are also iterative MapReduce, which are more complex with data analytics that requires good communication to work well. You look at which science applications are using clouds. There was now an old project called Venus C, which was using Azure in Europe, and they have 27 distinct applications they originally developed, and they were actually using nothing very sophisticated because at the time they were done, they did not have on Azure things like MapReduce implemented well. I ran a project called Future Grid, and a feature of the applications on Future Grid, but a large number coming from life science, partly because they were pleasingly parallel, and partly because this field is emerging. And we stress that clouds are likely to be used by the newer applications. Lilly Corporation is a commercial cloud user. That's a drug company, and it's using it to do simulations of possible drugs, their properties. Large-scale molecular dynamics. But there's not so much science use of clouds. There's a wonderful book by Ian Foster and Dennis Gannon, which has just come out, which describes this quite well. If you look at the Internet of Things, it's very well suited to the cloud because, again, everything is independent. When you click a button on your smartphone, that button clicking can be processed independently of everybody else's button. So every smartphone is independently processed on the cloud. And they're only linked when you analyze how many people click buttons together, which is not so often you do that type of work. But they also all themselves access shared data when they want to find out information that's uses shared data sets on the cloud. And there are 50 billion or so of these devices by 2020. Actually, I think the lower number, 24, is more likely to be true, but it's somewhere, it will soon be 50 billion. And that's a pretty large number, and even 24 billion is pretty large. And they will all send streams of information to the cloud, which will be processed with the other streams and turned into knowledge, and that will help the users of those devices. So the cloud is the controller and the source of wisdom for the things. We even saw that in the digital business in 2015 Gartner discussion, where we pointed out that actually the cloud was talking to things, not to people. Anyway, and another interesting is sort of sensor support. You have intelligent rivers, which are rivers covered with sensors, smart homes, homes covered with sensors, smart electrical grids where you monitor power use on a microscopic scale, ubiquitous cities, which are cities built with the vision that everything is electronic and that electronic signals are integrated together. And of course, robotics, a particular collection of sensors is a robot, and those robots will be cloud controlled. And some of these things will support science. And as I stressed many times, these things are naturally parallel and easy to do on a cloud. A cloud also is useful because of its on-demand nature. These things are not continuous. Sometimes the things will just switch off. Or if the thing is your smartphone, when you sleep, the smartphone is not so active. Also, the things are distributed, and that's what we mean by a grid. So you always have a grid of things. All right, here is a little picture of the fog. So we have our central cloud. It might have HPC systems attached to it for special purposes like deep learning. Then we have all our sensors spread around and the things, and including smartphones, email, and so on, and industrial Internet of Things, hospitals with all the medical instruments telling you how the patients are doing. Then, as well as the cloud, we have the fog, which is this band of computing near the devices. One question is how the fog is naturally used. Is the fog different from a cloud, or is it just a local cloud? My view is just a local cloud. It's too complicated to talk about supporting the fog in a very distinct way from the cloud. It's hard enough to write one program. You don't really want to write two, or maybe you have a hierarchical fog with a fog in every county and a bigger fog in every state and and so on, a hierarchical architecture. But that's complex. Okay, so we can discuss the fog in a little more detail here. I already made those remarks on the previous slide. One view of the fog is just everything. I mean, here's your car, it's colliding with the bus. So it wants to know how to best avoid the bus. So what it does, it sets up a network connection with the very powerful NVIDIA GPUs on the bus, and it uses those GPUs to process its data from its sensors and faster than it could on its own. And then having done it faster, it then is able to avoid collisions. So that's possible, but it's pretty difficult to rely on. I think I'd rather have enough computers in my own car so that there's enough computing to solve the problem locally. So the trouble about the fog is everything. You have administrative issues and ownership issues and relying on it issues, which make it rather difficult to see how that will work in practice. Smart homes are a little more plausible because homes are static, and maybe your neighbor doesn't mind if you borrow computing from the neighbor. I mean, actually, people sometimes borrow wireless signals from a neighbor when they want to connect to the internet. But I don't think that's also terribly viewed as terribly friendly or a good thing to do. There's security issues, among other things. Now, there are cases where it might work more plausibly. That is, when we have a traffic jam. If the computers and all the cars could get together and form a giant fog just to solve the problem of this collective problem, which is the collective traffic jam, that could be pretty useful. But then I don't think you're joining them together to get more computing. You're joining them together to share information. And we found out from the grid of previous years that managing systems across administrative domains is really hard. And it's a sort of trivial problem, but it's an insoluble trivial problem. And so that's why I like to view the fog as restricted to the compute systems that are in the same administrative domain and actually geographic, geographically attached to the devices they're servicing. Then we have a much easier system design, and that's already hard enough. And so the smart home actually does use computers outside the device, any one device, but those computers are owned by the home. And that's the problem that we're working on today. Streaming data is a very important category of application. It's very suited to clouds because clouds are on demand, and so you often have devices that stream data, and that streaming happens not continuously, but just every now and then. And then you can spin up your Kafka or a RabbitMQ instance to process that streaming data when it's needed, and then you send it to sleep when it's not. And otherwise, you get charged for the whole time you're running, and if you're running continuously, in case you stream, that could be inefficient. There are ways it could be efficient if you have enough, if you have shared resources and lots of devices are sharing a single streaming instance, but then you have concerns that that streaming instance may get overload sometimes if all those devices happen to communicate at the same time. So all of these applications, such as smartphones, tweeting, searching, they all produce streaming data, both going to the cloud and coming from the cloud. And Apache Storm and Heron are the technologies in HPC ABDS which are needed to address that problem. There's a whole sort of a computer science problem or an algorithm problem, which is when you have streaming data, you want to be able to do analytics like clustering, which is based on the data streamed in and just uses that data combined with a summary of the previous data to make decisions. The alternative is to view everything as a repository, so your data streams in, gets stuck in a repository, and sometimes later you do the analytics. That's sort of classic batch processing. The trouble with that is you may want the result immediately. You may want to discover that some anomaly is going on immediately. So the work we did in this area is published by NIST. We did Volume 3, Use Cases and Requirements. We also did Volume 8, Des Gregor, which was Cloud Mesh. And this has an extensive discussion of use cases, and we're now working on a new version of this. So as a result of that, we looked at these use cases, 51 of them initially, there are now a few more, and tried to classify them in all sorts of different ways, and we found eventually 64 different features, which are organized in 4 different so-called views. One view was all the things connected with the style of data. One view was the processing view. It's like the particular algorithm used and things like that. Another view was how the execution model was, whether it was dynamic or static, iterative or non-iterative, and what the size of the data was, what the size of the model was, and things like that. And then the final thing was the overall structure. Was it seasonally parallel in the fashion I just described? Was it MapReduce? Was it what I call map streaming, which is the data streaming case? Did it need a shared memory computer? And we discussed single program multiple data, SPMD. Is it SPMD or not? I pointed out most of them actually ended up being SPMD. Data fusion is a type of algorithm where lots of data sources are joined together, and so on. And workflow is orchestration, which we've also mentioned. Does it use workflow? Most of them did. Notice of the 51, 41 of them involved streaming, 26 were pleasingly parallel, and 25 involved MapReduce. So those categories are all very important. Here, just as one example, done in a little more detail, the problem architecture view, which had 12 features, which I've already gone through. Pleasingly parallel, classical MapReduce, map collective, I have a picture of this, map point-to-point, map streaming, shared memory. These were 6 critical architectures which describe the overall structure of the problem. SBMD, bulk synchronous processing I mentioned. That's a model where you do some computing, namely the map, then you do some communicating, then you do some computing and so on. Classic MPI style programming, fusion, data flow, agents. Agents are cases where you use a particular programming model with agents to implement it. And here are a picture of the 6 data analytics programming paradigms. I think this is a pretty important picture, although it's probably a little high level, sorry, a little too detailed for an introduction. Here we sort of sketch the structure of a problem which is pleasingly parallel. And the data comes in, it's processed independently, and some result comes out. So that's pleasingly parallel. It might be that you're applying an algorithm, a machine learning algorithm, separately on every event to try to classify the events, and that is a pleasingly parallel machine learning problem. MapReduce is where you do your maps, then you do some global operations such as reduction or gather to join the results of the maps together. And so that's just a variation of the pleasingly parallel where there's a final aggregated stage. In the case of particle physics analysis of the data from the CERN accelerator, actually most of the computing is pleasingly parallel. It's processing the data gathered from the devices on the accelerator. Then there's a final stage, which is actually computationally quite less significant, which involves producing histograms to try to collect the data together into a single source. Iterative MapReduce is classic parallel data analytics where you have maps, some sort of gather and broadcast, scatter operation, or actually a reduction is also possible. Then you go back to the beginning and things like clustering, any expectation maximization problem, linear algebra, the parallel linear algebra, or page rank, they all have this structure. Another structure is very important in graph problems, point to point. You have a bunch of nodes, and some of the nodes are connected, and you need to send messages between nodes. That's different from collective, where you need to send a message from one node to all nodes. This is the classic structure of simulations, and is also seen in data analytics for graph problems. Map streaming. This is the architecture of Apache Heron or Storm. We have data coming in here from the side, not from the top, as it was here. The data comes in the side, it gets stored on brokers, then we put in queues, and then we have long-running jobs going on forever, and they just fetch the data from the queues and process it. That's a very important architecture. Then we have the specialized architecture with shared memory, where we can't actually, we need to have the high performance of the shared memory to get decent performance. That's necessary possibly on some difficult graph algorithms. So an important aspect of big data, and when you're comparing with simulations, is to be a little careful in terminology. Then when you do almost any problem, you actually have some data and a model. So let's take an example. For clustering, the model is the centers. You want to find the centers of the cluster, maybe the radius of the cluster. The data are the points which are being clustered. Those points actually tend to be fixed. The model parameters of the centers varies as you iterate the algorithms, like k-means, and also the model parameters tend to be smaller in size than the data. So you have to be, then the reason why it's confusing is, at least historically, long time ago when we were mainly focusing on models, then doing a model for weather simulations, we used the term data to describe the parameters of the model. But we should actually separate data and model parameters. And we messed up in the past by not doing that. So here we've given some examples. Deep learning is an interesting example where the model is the network, which has weights for the nodes between the network, between the weight for the node links, and the model parameters are those node links, and the data is the images you use for training, or whatever you're using for training. So you can consider data as having a big data as having data, which is the data, and model, which is the way we parameterize the data. Simulations also have data and model, but for simulation, the model is typically the largest. There's often not a small amount of data. If I do quantum chromodynamics to try to understand protons, there's just half a dozen data values of data. Which dimension am I solving in? What's the size of the lattice? Whereas the model is enormous. We have to look at the core congruent fields defined on a whole set of mesh points. The data could be large when modern weather predictions, they use data assimilation, which is where you have a model, which is a very complex description of using the Navier-Stokes equations of the weather, and the data is coming in as a function of time and getting integrated. So you can also have another example with in case of big data, often the model is small. I mentioned k-means clustering, it tends to be small. If I do latent Dirichlet allocation, which is a topic model, then the model can actually be pretty big. Deep learning has a huge model. Actually, the model is probably bigger than the data. Dimension reduction, because it's reducing the data, dimension is actually quite small in model sizes. Data is almost always static. Model parameters always vary. As I told you in the past, we confuse them by using the word data to describe model parameters, but we shouldn't any longer do that. And these models, big data and simulations, they're basically parallel computing, and they have many similarities, and you can talk about them in the same language. So in order to get a good description of how to talk about things in the same language, we take use cases, we divide the use cases into data and model, we classify the use cases with these 64 so-called convergence diamonds. I gave you the picture. That was how actually we identified the importance of streaming data, pleasingly parallel, and global and local machine learning, because we used these features to classify the use cases and found lots of examples of both. In order to converge data, we recommend the high-performance computing enhanced big data stack with our 21 layers. And eventually we're moving towards what we call the HPC function as a service programming model, which we think will be a nice universal programming model for big data and simulations. And we're going to support it with serverless infrastructure, which, as we know, is going to be the way of the future. And then we have to look at hardware. Well, different problems will have different trade-offs and need different hardware. So whereas we can probably share the software, the hardware will, for optimality, be different for different problems. If we're just doing data management, the I/O performance is not, the communication performance is not so critical, and we can act accordingly. And we expect to use DevOps systems like our cloud mesh system to automate the deployment. And if we borrow some terminology from the cloud, we call that HPC Cloud 2.0. And then if we use the cognitive computing language, where the cognition is sort of the third step, that's HPC Cloud 3.0, which is sort of where we're all moving towards. HPC Cloud 3.0 supported with serverless infrastructure and a function as a service, an HPC enhanced programming model.